Alright guys, here's the video that I said I would make going through lesson 1 of chapter 11. I'm going to go through the entire lesson just so that we have kind of that for anybody who's gone, either say today, tomorrow, say whatever. I figure it's not a bad thing to be able to kind of look back on. I would say if you guys can get through the first couple kind of examples, so that's a really, really good start, say, because again, this is going to be a 2-day lesson at minimum. You will kind of hopefully notice some things that are similar to some of the like hypothesis testing that we did in chapter 10. Like we're gonna say try to still determine whether we reject a null hypothesis or not. We're still gonna try to get like z-scores, t-scores, things like that. It's just now we're gonna be using or we're gonna be working within kind of a realm of like say 2 populations or treatments. So we've got like 2 groups of data that might have different means, that might have different standard deviations, that might have different sample sizes. And so we have to kind of work with those things. So our formulas are going to be a bit more intense, I guess, for lack of a better term. And then another bigger change is our degrees of freedom. Unfortunately, degrees of freedom is not going to just be n minus 1 anymore. So there's a bit more math that kind of goes into that because, again, we might have 2 samples of different size. So we can't just take n minus 1 necessarily. So example here, we might be looking at, say, sample data for 2 different populations. So maybe we want to look at mean cost of textbooks for an engineering college versus an educational college, or maybe a science department versus an English department. Or something like that, and we want to maybe try to prove that one's more expensive than the other or not, or maybe we want to see, okay, which class rank is higher, boys versus girls, so maybe we work under the assumption that they're the same, and then we try to prove one is less than or greater than, or something like that. And so the packet that hopefully you have has all of these formulas and stuff. Unfortunately, I didn't maybe get many examples or really any in there to try to kind of save a little bit of paper at least. But all of these formulas you should have, so I'm not going to ask you guys to memorize those. Anything you want to add to that note packet, absolutely go for it. So if you want to find space for the examples to work them in there, go for it. I'm going to try to kind of make notes of like the main things here, or where some of these formulas kind of come into play maybe a little bit more often. And so like this first one here, say this part here, this say mu1 minus mu2. And this is one thing we're going to see a lot within this kind of situation dealing with 2 data sets. It's going to be a lot of, say, little subscript letters, so like that 1 and that 2. It's going to be a lot of that stuff trying to like distinguish between one data set and the other. So like this would be the mean of your first data set. This would be the mean of your second data set. But a lot of times this piece kind of comes in either with HO or HA. I would say normally it's probably going to be your like HO, null hypothesis, because we'll work under the assumption that like 2 data sets are kind of the same. And so that'll kind of come into play with like that hypothesized value. And then say the variance piece here, we tend to not use that as much. Say that's more our book just trying to say, okay, here's the formula for variance. The one that we tend to use more often is standard deviation. So this thing here, we're going to see quite a bit within, say, a couple different kind of areas. Okay. And again, say like N1, N2, that's just like the sample size of your first data set, sample size of your second data set. This thing here is like the variance of your first data set, variance of your second data set. Okay. What we're going to kind of be able to find, or what we're going to be able to like maybe usually be given, we'll a lot of times be able to either find or have access to like standard deviation of our first data set or standard deviation of our second. So like we'll have that, which we'll then be able to kind of plug in for the squared divided by our N1, okay, for both of those. And so, like I said, it's going to be some similar kind of processes. It's just our formulas are going to be a little bit crazier, okay, at times. say this third part down here, if N1 and N2 are both large, so we still have those assumptions if we're dealing with mean. The big two are that our sample is random or that it's representative of our greater population. Okay, and we'll see that here in an example later on. And then again, that our samples are both large. Okay, so we want our samples greater than or equal to 30, say just like we had in the previous, say chapter, previous sections, we still want those things to hopefully be true, to kind of have this assumption that our data is normal. Okay, quote unquote normal. Say normal in the sense that it follows that, say, normal distribution curve. And that's not a great drawing of it, but so I think you guys get what I'm saying. Okay. Okay, so the big formula, okay, that we're going to be, say, using a little bit here, say, is this z-score thing, okay, where we've got z equals x bar, or x1 bar minus x2 bar minus mu1 minus mu2 over that square root, say all that, say that thing that I just kind of highlighted there. Again, we're going to be able to find numbers for like this thing, this thing, this thing, this thing, this thing, this thing. Usually, a lot of times we work under the assumption that mu1 equals mu2. So a lot of times this whole thing ends up being 0, which is kind of nice. Say simplifies that piece a little bit. Again, it's not a guarantee every single time, but it's pretty darn consistent. So a lot of it's going to be kind of identifying these things, being able to pull this information out of kind of context, different examples, things like that. Say, and then kind of work within, say this formula, okay, to find like a z-score or a t-score or something like that. Okay. And so if we look at kind of our first example here, okay, and I'll kind of give you an idea. So I've got everything kind of written down right away, so if you need to pause this as we kind of get into the example, go for it. But I wanted to have everything written down just so that you don't have to wait for me to like type in things or write things down, and I can maybe go a little bit quicker for you. And hopefully also kind of take out any like silly mistakes that I might make. But if we are trying to figure out if wait times are different, so researchers observed wait times in coffee shops in Boston. Both wait time and gender of the customer were observed. The mean wait time for a sample of 145 male customers was 85.2 seconds. The mean wait time for a sample of 141 female customers was 75 seconds. Standard deviation of wait times for the population of male and female wait times was estimated to be 50 seconds and 75 seconds, respectively. For purposes of this exercise, consider that these samples represent the population of wait times for males and females in coffee shops in Boston. Is there convincing evidence to show that wait time differs for males and females in coffee shops in Boston? That is a ton of words. Let's try to kind of pull some key information out of this. So we've got mean wait time for 145 males was 85.2. So like in this case, our N for M, okay, our sample size of M males is like 145. The X bar for males was 85.2. And then N females, if we look at that was, so we had a sample of 141 females, so NF would be 141. X bar F was that 75 seconds. And then we were also given standard deviation of males and females. So like I said, a lot of subscripts are going to get used to try to differentiate between, like in this case, male and female groups. And we were given that was 50 and 75 respectively. So that'd be 50 and that'd be 75. Okay, so trying to kind of piece through all of that. And like I said, I've already got a lot of that written down here. Okay, so we've got, again, sample size, average, standard deviation of both males and females. The hypothesis that we are going to kind of work under here, okay, our null hypothesis is that if I subtracted my mean or my average wait time for males and my average wait time for females, if I subtract those two, I should get 0. Okay, because what that's implying is that, say, the average wait time for males is the average wait time for females. Okay, we just kind of subtract this part over here to get average of males minus average of females equals 0. Okay, and if we're trying to prove in this example, okay, is there convincing evidence to show that the wait time differs? Okay, doesn't say one is less than, one is greater than. So we're not trying to like prove that. We're just trying to prove that they're not the same. So then my average of males minus my average of females would not be 0. Okay, again, I'm not claiming one specifically is bigger than the other. I'm just saying they're going to be different. So if I subtracted them, I'd not get 0. Just like chapter 10, if we aren't given a significance level or aren't given an alpha value, we're going to assume it's 0.1. So here I just made a note that alpha is equal to 0.1. Before, say we maybe get too far here, again, we should check the whole random sample n greater than or equal to 30 for both kind of groups here. And we weren't given the random piece, I don't believe, but we are given that for purposes, consider these samples to represent the population. Okay, so they are representative, which is ultimately what we want. Okay, saying usually that randomness kind of gives us that representative aspect. Okay, and then say our sample size, we're both definitely over 30, so we can kind of check off that too. Okay, now within this, okay, we're going to go find a t-value here, okay, because t-values are kind of based on degrees of freedom, sample size, that sort of stuff. And again, because we have different sample sizes, this is going to get a little bit kind of more complicated, but we'll try to kind of go step by step here. So this is the formula that's in your packet, say the x1 bar minus x2 bar, that whole thing. Again, this piece here is just going to be 0, okay, say that's kind of coming from this part, okay, and so again, a lot of this we have numbers for, like we know everything here, 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 and here, and we know that this ultimately equals 0, so all of this we're going to be able to plug something in. Okay, so if we start kind of doing that, say my 85.2 is my average for males, my 75 is my average for females, okay, again, minus the assumption that they're the same, so the difference of them would be 0. And then underneath there, I've got that square root of that 50 is my standard deviation of male, the 145 is my sample size for male, plus 75 is the standard deviation for female, and the 141 is my sample size for female. Okay, so we're basically doing a fraction for the male, fraction for the female. And if we kind of work this through, okay, the 85.2 minus 75, that gets me 10.2 on the top part. That bottom fraction or square roots, say ends up being 7.56. And so if I divide those, I get 1.35 for a t-value. Okay, so I get t equals 1.35. And now normally what we would have done, say if we'd gotten a t-value for one data set, is we would have gone to our t area table with the degrees of freedom on top, that t-value on the left there. Well, degrees of freedom, like I said, is a little bit tougher to find now because we don't have just one sample size, so we can't just do n minus 1. So we have this entirely different formula now for degrees of freedom, which is v1 plus v2 squared over these two little fraction things, v1 squared over n1 minus 1 plus v2 squared over n2 minus 1. Don't worry about necessarily scribbling that down. It comes up a little later in our notes. We probably should have put these in a little bit of a different order here. But this piece right here is your degrees of freedom formula. And they even have over here, how do we find V1? How do we find V2? Okay. saying S1, and maybe this is a little mistake I made before. Say that S1 is like your standard deviation for data set 1. Okay, so maybe up here, say I shouldn't have used the like sigma notation. I maybe should have said S, M, and SF, but say we can keep it like that, say for now. Okay, and because our formulas kind of seemingly switch between like samples and population notations, and it's I will admit a little confusing at times. But our V's come from taking our standard deviation squared divided by our sample size for each one. So this first fraction here, this is going to be my V like for the male data, and then this will be my V for female data. So that 50 squared over 145 gets me 17.24. And then the 75 squared over 141 for the female gives me 39.89. And I'm going to take those and we're going to plug them in not only up here and here, but we'll also plug them in down here and down here. And again, N1, N2 are just sample sizes, so we already know those pieces. So if we've got degrees of freedom, is going to be that 17.24 plus the 39.89 that we just found, those added squared over that, all of that stuff on the bottom there. So just plugging in the V values that we just found, say up here. If we work all that through, which I know that's a lot of like plugging into a calculator, stuff like that. That top part ends up being 3,263.84, and then the bottom ends up being 13.43. And so ultimately we get about 243.02. Excuse me, which is basically 243. And that's going to be our degrees of freedom. And so now that we have a T value, that 1.35, and now that we have a degree of freedom, 243, now we can go to that T table. And so we're basically trying to ask the probability that T is not equal to 1.35. And kind of a reminder here that when it was not equal to, this is a two-tail test. So ultimately we're going to have to multiply by 2 at some point here. And we do that after we go to our T table. And so if I looked at our table correctly, say I think I went to the, there's a column for 120 degrees of freedom, because I was about as close as I could get. And I was debating between the 120 degrees of freedom and then like the infinity one. There was like a 0.001 difference, which isn't going to make that big of a difference. So whichever one you kind of went with, so you're ultimately going to get something around 1.62, 1.64, say right around there. And this is going to be our p-value, kind of like we were finding p-values in chapter 10. The p-values are what we ultimately compare to alpha. So what we're going to kind of do here is we're going to take that 0.164 or 162 if you went with the infinity one. Say we're going to say that is greater than 0.1, which is our alpha. Okay. And we are going to say, because of that, we do not reject the null hypothesis. So because we do not reject the null hypothesis, if I can kind of go back up here to our hypotheses, we are not rejecting this one. So we're kind of accepting that one. We're saying this one, say, is not so good. Okay, so we're saying the data supports this one, which is kind of saying this piece up here, that the wait time for males is the same as females. Okay, so we can say data supports that the average of males minus the average of, I should have said females there, is equal to 0. So we can say data supports that wait times are the same. Okay, so again, bigger picture theory is very similar to what we did in chapter 10. It's just the math, and I don't want to make this sound like, oh, this is all super easy. I know it's not. There's a lot of kind of moving parts here. There's a lot of notation. There's a lot of little places that we can go wrong. But the goal is ultimately the same, to try to get a t value or a z value, find maybe degrees of freedom, okay, ultimately get a p value to compare to alpha to try to reject or not reject, say, a hypothesis that we made. Okay, that's still ultimately the goal. Okay. So here again is that degree of freedom formula that we probably should have maybe had a little bit earlier in the notes there, but hopefully so that makes a little bit of sense there, or at least kind of makes sense how we use it or how we calculated it. And again, here's kind of how we found, say, that t value, which is really, really similar to that z value or that z formula from before. Okay, so this maybe is the one I should have highlighted more as the one we'll use probably more often. Okay, so those are some big ones that we'll kind of see quite a bit here. Okay. Again, say those assumptions are kind of the same thing. Say degrees of freedom, page 764. Again, the 764 is, I tried to give you that table, okay, rather than always having to have you have your book or flip back and forth on that. So you can use your table that I gave you, the second one, not the one dealing with the confidence intervals, the one that has degrees of freedom on the top part there. So we can use that one. Okay. So if we look at kind of another example, say we're trying to figure out in this case if GPA from people who use Facebook is different than people who do not use Facebook. So we have a sample of 141 college students who use Facebook were asked to report his or her college GPA. College GPA was also reported for each person in a sample of 68 students who do not use Facebook. So one question that the researchers were hoping to answer is whether the mean college GPA for students who uses Facebook is lower than the mean college GPA of students who do not. So this one is kind of deciding we want to try to prove lower than, not the just differs from. So we're going to be able to maybe be a little bit more detailed there. Two samples were independently selected from a student at large public Midwestern University. Although the samples were not selected at random, they were selected to be representative of the two populations. Okay, so even though they say it wasn't random, they were strategic enough that they were able to get something representative of the larger groups, which is, again, ultimately what we want here. Okay, and then they gave us kind of this information in a little bit of a table here. So they gave us sample size, like for Facebook, and then not Facebook, Facebook, not Facebook, and so on. So they gave us sample size, mean, standard deviation, which is exactly what we need, say, for all these things. And again, we're going to try to prove or try to determine whether GPA is lower for Facebook or not Facebook, or and then here they give us, say we want to use a 0.05 level of significance. So if we just kind of try to take what we're given and just try to organize this a little bit first. So for me, the subscript part in this example, I just used F for Facebook users and then N for not Facebook. I didn't really want to do NF for not Facebook just because that would have been even messier than maybe what it already is. And so we got our sample size of 141 and 68 for each. We got our averages, 3.06 and 3.82. And then our standard deviation. And again, maybe I should have put these as... So maybe we should have put these as S, F, and S. And kind of like they have here. So I'll make that change real quick. So again, we were given the representative. Our sample sizes are bigger, so check there. Our hypothesis that we're kind of working with, again, we're going to work under the assumption that the GPAs are the same. Okay, so that the average for Facebook is equal to the average for not, and we're trying to prove that the average for Facebook is less than the average for non-Facebook users. Okay, and again, we want to use that alpha level of 0.05 in this case. And so, again, we're going to go find that t statistic. So here, again, is your formula that we're going to use. And so I'm going to go with the 3.06 minus the 3.82 minus the 0, because, again, this piece here is your same Facebook equals average for knots, which would kind of imply that Facebook minus not Facebook would be 0, which is this piece here. Okay, so that's where that 0 is coming from, and then we got our standard deviations and sample size plugged in on the bottom there. Okay, again, if it helps to like pause this and kind of write things down and make sure you got stuff, go for it. But that top part, say, should be negative 0.76, and then the whole bottom part should be 0.094, which if we divide those, we get negative 8.08, say, for a t-value. And now some of you might already be getting a little ahead of me here, and that's okay, say, in this case. Some of you might look at that t-value and think, well, that is way too big for the table that we have, because it's way bigger than 4. And so we can just assume that our value is 0. And I'm not going to disagree with you here. I do want to still try to take this opportunity to just look at that degree of freedom formula again, though, because, again, we're going to need to be able to find that, say, from time to time. And so, again, it's this thing here. Okay, and again, find that V for Facebook, V not Facebook. Those are these things here where you take standard deviation squared divided by the sample size. So for Facebook, it ends up being 0.0064. And then for the not Facebook users, it ends up being 0.0025. And if we plug those things in, again, I know this looks kind of crazy, and we get some really, really, really small decimals. Within this formula here, we end up with a degree of freedom of 205.18, which I would probably just round to 205. Okay, which again, t-value of negative 8.08, degree of freedom 205. The degree of freedom in this case wasn't going to matter. Say we were going to get a area of 0 anyway, which again, that is our p-value, which is ultimately what we want to compare to alpha. And so in this case, 0 is less than 0.05. And so that we're able to say reject our null hypothesis. So we're going to say data supports that GPA for Facebook users is lower than non-users. Okay, because again, if we're going to reject H0, okay, we're going to say this one is no good, then we're kind of accepting, or at least we're supporting that other one that says Facebook is less than non-Facebook. Okay, is ultimately what our conclusion is kind of coming to here. Okay. Okay, again, hopefully there's at least some feelings of familiarity within like the hypothesis testing and getting P and comparing to alpha and those sort of things. I know the actual calculations here are a little bit tougher, and there's kind of like some side missions or side quests going on. At least maybe more than in previous chapters, but so I'm hoping we're at least feeling okay so far. The last thing I kind of want to kind of get to here is kind of taking what we did in chapter 10 and then even go back a little bit further. So this is just kind of, again, the assumptions and the like hypothesized value and stuff like that. So I'm going to kind of skip over that. We're going to try to take what we've done kind of recently and go even back a little bit further to kind of finding confidence intervals. Okay, so we're going to try to find confidence interval, say, with 2 data sets now. Okay, and so again, we should have those assumptions of random samples n greater than or equal to 30, or somehow say be given that it's normal. Okay, again, that's the piece that we're looking for. But then our formula, and again, I'm hoping this looks at least kind of familiar to the confidence interval formulas that we did back in chapter 9. So we had, before it was just X bar, but now since we have two data sets, we're going to take X bar for data set 1 minus X bar for data set 2. Say we're still going to use a T critical value. Say we're going to have to find, again, we're going to need degrees of freedom for that, which we're going to find kind of the same way as before. So again, I understand a little bit more to that in this case. And then say we've got our kind of standard deviation formula there at the end. Okay, and again, our V1, V2, or our V values for each data set are the same as kind of what we did before. And then again, this is going to give us two values, two numbers in the end, because we've got a plus minus there. So we'll, again, this is going to turn into a number in the end, plus or minus. This whole thing should end up turning into a number. Okay, and so ultimately we're going to get two numbers from the plus minus piece of it, which will give us our confidence interval, our range of values. Okay, so let's actually try throwing some numbers into this thing here, and maybe it'll hopefully make a little bit more sense. But we've got, is injecting medical cement effective in reducing pain for people who have suffered fractured vertebrae? A study suggests an experiment to compare patients who underwent vertebroplasty, the injection of the cement, say to patients in a placebo group who underwent a fake procedure in which no cement was actually injected. Because the placebo procedure was similar to the vertebroplasty procedure, except for the actual injection of the cement, patients participating in the experiment were not aware of which treatment they received. All patients were asked to rate their pain at 3 different times: 3 days, 14 days, and 1 month after the procedure. And they give us a summary of statistics here. So they give us sample size for each group. They give us mean standard deviation for each group after the 3 day, 14 days, 1 month time frame. And what we are going to try to do is we are going to construct a 95% confidence interval for 3 days following the procedure. Okay, so that's why I kind of have that top part boxed in. So like this stuff down here isn't going to matter because we're just worrying about 3 days following the procedure. And that was just the duration I picked. Okay, we could have done 14 days, we could have done 1 month, and we just would have used those data values instead. And so if we kind of, again, go up and check our assumptions, okay, random, say n, sample size were both bigger than 30, so all of that was fine. Again, sample size 68, 63. Say the average for the vertebroplasty and the placebo, or the 4.2 and the 3.9 standard deviation for each. Say right away, because I knew we were going to need the T critical value, and to find T critical value, we were going to need degrees of freedom. So I went and found the V numbers for each group that we're going to need in that degree of freedom formula. So just took the standard deviation for each squared, divided by its kind of respective sample size, which gave me 0.115 and 0.133 for each one. And so then again, use that in finding degrees of freedom here. And so we get 0.115 plus 0.133 squared over, say, those two little fractions, which is going to get us 0.062 over 0.00048, which ultimately gets us 129.17, which I would say we can be pretty comfortable calling that 129. Okay. Now, since we're going back to confidence intervals, say we're going to need that first T table that I gave you that has the confidence levels on the top and the degrees of freedom going down the left side. I know, say, the tables kind of get a little confusing. Okay, which one do I need when between the Z table and the two T tables? Okay, now we need confidence interval. And so with a 95% confidence interval, degree of freedom 129, I think I used the 100 row. if I looked at it correctly, I got a t-value of 1.984, say, from that table, which then that is ultimately, and if I kind of go back up here, is letting me find this thing, because this piece and this piece we were given in the problem. This part, this part, this part, this part, we were all given in the problem. So all of the math so far has been just finding that thing. Okay. And so now that we have it, we can go down here, okay, and use that same formula. And so we get the 4.2 minus the 3.9. Generally speaking, there we go bigger minus smaller. If you're wondering, okay, does order matter? Generally, we go bigger number minus smaller number. And then we go plus or minus, that t critical was the 1.94 times the square root of, say, those standard deviations that we were given and the sample sizes that we were given. And ultimately that fraction piece. And one thing I did want to kind of notice here, if you kind of point out here one thing, you notice that value there is just that 0.115 that we found earlier. Same thing here, that's the 0.133. Those are like the VF, or not F, VV for the vertoplasty and the VP for placebo. So if you wanted to just kind of jump to that point right there, you absolutely could. But then that whole square root ends up just being 0.498 anyway. And if you do that times the 1.984, we get 0.988. And now we can do that 0.3 plus, 0.3 minus. And ultimately we get values of 1.288 and negative 0.688. And that is going to ultimately be our confidence interval. Okay. Okay. So hopefully this makes, I'm not even going to say makes a little bit of sense. I'm hoping that we at least just feel a little bit comfortable within finding some of these things. Like maybe there's a little bit of familiarity within like this part here. I understand this like new degree of freedom and these new V numbers or values that might still be like, holy cow, where the heck did these things come from? And I completely understand that. Say if you have any questions, say throughout this whole lesson or anything, make note of them, write them down, say, let me know. I'm happy to help you out with any of this. But I'm hoping at least by having a video now, you can go back and if you want to rewatch and pause and rewind and do whatever you want with this, I'm hoping that is at least a nice resource to kind of have. If there's anything more that I can do to help you out though, again, please do not hesitate to ask. Okay, I want to make sure we can kind of finish the class strong, and I know this is not easy stuff, but say the assignment for lesson 1, and again, this is minimum 2 days, possibly even 3, we'll kind of see how it goes, is going to be page 575, 578, 1, 2, 4, 6, 7, 10, 12, 15. Okay. Again, hopefully this helps a little bit. Say again, pause, rewind, rewatch, whatever, ask questions. Okay, if there's anything that like I maybe said that didn't match up with the video and I just kind of overlooked at it,